Okay, so now we move on to functions of random variables. We might have a situation in which we're measuring something directly that's a random variable x, but we're interested in some function of x. So we want to know how we can handle that. Okay. So let's start with a few examples. Okay. So if we flip a fair coin, we assign the random variable x to take the value +1 if we get an h, and we assign the random variable the value of -1 if we get a t. Okay? All right, so let me ask you, after the experiment takes place, what's the probability that x is taking the value +1? Let's say it's a fair coin, 1/2, right? Or -1, 1/2, right? Okay. All right, so how do we work that out? Okay, x is going to take the value +1 if and only if we get an h. So the probability that x takes the value +1 is the probability that you got an h. Fair coin, it would be 1/2. Okay. What about x taking the value -1 after the experiment? It's also 1/2. Why? Because the probability that x took the value -1 is the same. That happens if and only if you got a t, and the probability of getting a t if it's a fair coin is 1/2. Okay, so we're used to doing something like this. And once we have a discrete random variable, we can think about finding its PMF, finding its expectation, finding its variance, right? That requires the PMF. And right, so the PMF for x is defined as that it takes the value 1/2 for x equals +1, it takes the value 1/2 for x equals -1, and it can't take any other value. Okay? So that's the PMF for this random variable. Okay, now I'm going to define a second random variable as a function of the first random variable. Okay? So the experiment gives me x, and then I do some manipulation of x to give me y. So let's say we have a second random variable, y equals x squared. Right? Now, this is a random variable. It's a function of a random variable, so it is a random variable. Now, it's going to have its own PMF, its own expectation, its own variance, right? So we would like to know, if I know how to get from x to y, are there some rules that can tell me how to get from, say, the PMF of x, and I should be able to get the PMF of y, for example. It should help me get the PMF of y. Okay. Let me ask you. Y is equal to x squared. What are the possible values for x? +1 and -1. So what are the possible values for y? Right? The only allowed value for y is 1. Okay? So once again, x can only take the values +1 and -1. Then y can take the values y equals x +1 squared and -1 squared, which are both +1. Okay? So now, how would you write the PMF? How would you define the PMF for y? Okay, well, all right. The PMF for y is defined by saying, what's the probability that the random variable y takes the value small y? Okay, that's the probability that y is equal to y. Okay? Now, what values can y take? It can only take the value 1, right? For y equals 1, what's the probability that the random variable y is equal to 1? Well, it's certainly equal to 1. And it can't, the probability that the random variable y takes any other value is 0. Okay? So that's how you would write the PMF for y. Okay? The CMF?
That would be the expectation, right?
No, the CMF is not the expectation.
We just sum all of the probabilities.
Well,
That gives the CMF.
okay, well, all right. If we wanted the, yeah, if we wanted the CMF, okay, then that's basically, okay, the probability that y, the random variable y, takes a value less than or equal to y. Okay? So, how does this work? Okay, well, let's try a few values. What's the probability that y is less than 3? What's the probability that y is less than or equal to 2? 1. Yeah. What's the probability that y is less than or equal to 1? 1. What's the probability that y is less than or equal to 0.99? 0. Okay. Is that enough hints that you can tell me?
Okay, so instead of saying y equals to 1, you just define it piecewise. So
Yeah, it'll have to be defined piecewise.
so if y is less than 1, then the probability is 0.
Okay. Well. All right, so if you're going from minus infinity, if y is anywhere to the left of 1, what's the probability? 0. Okay? And then the probability is less than or equal to some number, which is 1 or bigger, is 1.
I have one tiny question.
Yes?
The PMF also gives probability and the CMF also.
Okay, right? The probability for, all right, the PMF is the probability that the random variable takes a particular value. That's what it tells us. The CMF for a discrete random variable gives us the probability that the random variable takes a value less than or equal to some number. Okay?
One last.
Yes?
Sorry, I know this is off the
Yeah.
topic.
No, yes. No.
I just want to clarify for the question.
Yes.
So the PDF then gives the probability of a continuous
Right. If you have a continuous random variable, it has a PDF rather than a PMF, and you integrate, it gives you a probability density. So you integrate the probability density from A to B to give you the probability that the random variable takes some value within the interval from A to B. Okay?
Will be integrated to get the...
So you have to, right, and then you have to integrate that to get the CDF, because the CDF gives you the probability. When you integrate the PDF to get the CDF, it gives you the probability that the random variable takes some value somewhere between minus infinity and the input to the CDF. Okay? All right.
So for discrete variables, we can directly get probabilities from PDF as well as CDF, but from PMF and CMF.
Yes.
Yes, ones we can only integrate and get probabilities.
Right. The PMF for a discrete random variable gives you a probability. The PDF for a continuous random variable gives you a probability density, and you have to integrate to find a probability of the random variable lying in an interval. Okay? Okay. All right, another example. I have a random variable, x. It has a PMF, which takes values 3/4 times 1/4 to the x minus 1 for x equals 1, 2, 3, and so on. And x is not allowed to take any other value except 1, 2, 3, and so on. Okay? So we've defined a PMF for a random variable x. Okay? Now, I'm going to define y equals x squared. Okay? So if y equals x squared, then what values can y take? Okay. X can take values, we said 1, 2, 3, 4, and so on. Y equals x squared. And so that can take values 1 squared, 2 squared, 3 squared, 4 squared, and so on. Okay? So if x takes values 1, 2, 3, 4, 5 with some probabilities, then y takes those squared values with the same probabilities, right? Right? So what's the probability that y is equal to 2 squared? Okay. All right, all right. What is the probability that y is equal to 2 squared? Well, for y to be 2 squared, what does x have to be? X has to be 2. So the probability that y is equal to 2 squared, the probability that y is equal to 2 squared, that's the probability that x is equal to 2. Okay, I mean, we could have said if y is equal to 2 squared, then x could be plus or minus 2, but it can't because x is only taking these positive values, right? So, I mean, just be careful. If you're dealing with squares or something where there could be multiple values, then just be a little bit careful, right? There's a reason I'm saying x is equal to 2 and not x is equal to minus 2, That's because we're not allowing any negative values. Okay. So that's the probability that x is equal to 2. What's the probability that x is equal to 2? It's 3/4 1 over 4 to the power 2 minus 1, according to that formula. Right? Okay. What's the probability that y is equal to 37? Y. 0. Why? Okay. Because y only takes squares of positive integer values. Okay. So y cannot be equal to 37. Okay. What's the probability that y equals minus 7? 0. Minus 7 is not on that list of allowed values. Okay. What's the probability that y is equal to 9? All right. Right. In order for y to be equal to 9, which is 3 squared, x has to be equal to 3. So whatever the probability of 3 was in that PMF, I've forgotten.
3 over 4 into 6.
Okay. Okay. So y equals 9. Y equals x squared, so x equals minus 3 or plus 3, but there are no negative numbers in the list for x, allowed values for x. So that's the probability that x is equal to 3. Well, that's given by the PMF for x. You see, if these probabilities that we're working out for y are related to the probabilities that we're working out for x, which are given by the PMF for x. So we might be able to write the PMF for y taking some help from the PMF for x. Okay, so that's equal to the PMF for x evaluated at 3. And the formula in that we gave when we defined the function, that's 3/4 times 1/4 to the 3 minus 1. Okay. Okay. Any questions so far? Okay. The probability that y is equal to n squared for n some positive integer. What's that? Yeah. The probability that y equals n squared is that y is only equal to n squared if x was equal to the positive integer n. And the probability that x is equal to n is given by that formula in the PMF for x. Okay. So once again, the probabilities for y can be found in terms of the probabilities for x, which is given by the PMF for x. All right. So finally, let's state the PMF for y, which is equal to x squared. Okay. So this is the probability that the random variable takes the value y. Okay. So this is the probability that y takes some value. Y was defined to be x squared. Okay. And then if y equals x squared, then x is equal to the square root of y. Right? Okay. Be a little bit careful when you're taking square roots. Don't take the square root of a negative number or something like that. So when you specify your PMF, you're going to have to make sure of that. Okay? So, if the PMF for y is defined as the PMF of x evaluated at root y, okay? Well, that was 3/4 times 1/4 to the, well, That was supposed to be an x minus 1 there, but x is root y. So root y minus 1. For y equal what? For y equal this list of perfect squares. And y is not allowed to take any other values. Okay? Okay? Always your PMF has to be defined in such a way that for whatever real number I put as an input to the PMF, it should be defined for that. Right? I should be able to work out what the PMF evaluated at that number is. Okay, so the PMF of a discrete random variable can help us find the PMF for a function of that random variable. Okay. Now, sometimes, so that one we had to think a little bit about what y was. Okay. When the function, when y is a one-to-one function of x, then we have a straightforward formula. Okay? Otherwise, you have to think a little bit more. But anyways, what's a one-to-one function? Okay, so, right? A function f is one-to-one if f of a equals f of b necessarily implies that a is equal to b. Okay? Another word for one-to-one is we say that f is injective, or we say f is an injection, or we say it's one-to-one. Okay? I'll try to use the terminology one-to-one consistently, but if I say injection or injective, you should understand what I mean. Okay? So let's be a little bit clear on what we mean by one-to-one, because you can't use this formula that we're going to derive if it's not one-to-one. Okay, so we have to be clear on what functions are one-to-one. Okay, so let's just do a few examples. So f sends reals to reals, defined by f of x equals x cubed. That's one-to-one, right? If I drew a horizontal line through the graph of this function, that line would hit only 1 point. It wouldn't hit 2 points. Okay. F sends integers to integers, defined by f of x equals x squared. I say that that function is not one-to-one. Can you tell me why? Okay. It doesn't satisfy the horizontal line test. You can have two inputs, two different inputs, which evaluate to the same output. So for example, f of minus 2 is 4, and f of plus 2 is also 4. So the function is not one-to-one. Okay, so you couldn't apply this formula that we're going to derive. Okay, how about this? F sends positive integers to positive integers. F of x equals x squared. Okay, so f of x is x squared, and f of minus x would be x squared, but minus x is not in the domain of that function, right? So what would the graph might look like this, right? And if we draw a horizontal line, we're only going to hit 1 point on the graph. Okay. Okay, so the idea is that if we're satisfied that the function is one-to-one, we can find, and we have the PMF for x, then we can find the PMF for f of x. Okay, so basically the idea is f is one-to-one. Now think of f as just restricted to mapping onto its range. Then f is one-to-one and onto. And all functions which are one-to-one and onto have inverse functions. Right? So let's say I have a map U which is one-to-one. X is a discrete random variable. Then it has its own f of x, f sub x, its PMF. Y is equal to, we define a new random variable as a function of x, y equals u of x. Let's say that that's one-to-one. Now, since u is invertible, let's say it has an inverse v, right? So y equals u of x, and x is equal to v of y, right? Then where we see x, we can replace it by v of y. Or where we see, right? Okay, so we'll see an example. In fact, we already did this in the previous example, basically, right? We had y is equal to x squared, and what showed up in our PMF for y? The square root showed up, right? Okay, so basically, here's the formula then, which we did a particular example of in the previous example. That says that if you want the PMF for y evaluated at y is equal to the PMF for x evaluated at, well, x is equal to v of y. Okay, the inverse transformation. Okay, so here we go. Let's look again. I claim, right, that this was a particular example. So let's look at that example again. So we had our PMF, right, and for x, right. Now y equals x squared. Since x is 1, 2, 3, the positive integers, we said that the map from the positive, the squaring map from the positive integers to the, right, was one-to-one. Okay? So, y equals, so y equals x squared, and x is equal to root of y. It would be a problem if we could say plus or minus root of y, but there's no minuses involved here, right? Right? X is never is not a negative number ever. Right? So this is the inverse transformation that we're talking about, the v of y, right? Okay, so f sub y of y is given by f sub x of, right? Don't write x. X is the same as the root of y. Okay. So this is equal to 3/4 times 1/4 to the what? X is, in terms of y, the root of y. So root of y minus 1 for root of y equal to 1, 2, 3, and so on, and 0. Otherwise, okay? So in the case of a one-to-one discrete random variable with a one-to-one transformation, we can take the inverse map and we can get the PMF for y. We can derive it from the PMF for x with a little algebra applied to the PMF for x. Okay? All right. Are there any questions on that one? All right. Okay. So let's say I have a random variable x. It has a PMF f sub x. Defined in this way, f sub x is equal to lambda to the k, e to the negative lambda over k factorial. And k takes values 0, 1, 2, 3. And it takes no other values. Let's say y equals 3 times x. I asked you to define f sub y. Okay. All right, can we use that? Can we use that formula? I mean, even if we couldn't use the formula, we can still think our way through the problem. But if there's a formula handy, let's use it. So, is that a one-to-one transformation? It is? Why?
Because every value of x maps to only one value of y.
Right. If I have right, so f of a is equal to 3a, and f of b is equal to 3b, and if these two are equal, it necessarily follows that a is equal to b. Right? So that's a one-to-one transformation. Oh, good. Now I can use my formula. Okay, what's the inverse transformation? If y equals 3x, then x is equal to 1/3 y. Okay. All right. So, f sub y of y, the PMF for y evaluated at y, is equal to the PMF for x evaluated at the inverse transformation. This time, the inverse transformation is y over 3. Okay? Okay, so k is taking values y over 3. Sorry. Y is taking values 3k for k equals 0, 1, 2, 3. So y is taking values 0, 3, 6, 9. So e to the negative lambda. Lambda to the k would be y over 3. Over k factorial would be y over 3 factorial. And 0 is as before. Okay. All right. Any questions about that one? Okay. Let's say x can take values -1, 0, and 1 with probability 1/3, and cannot take any other values. We had the PMF for x is like on the screen. Let y be defined by y equals 2x minus 1. Okay. Find f sub y. Okay. Give it a try. Okay, so we're going to use the formula. Is it 1 to 1? Yeah, so y equals 2x minus 1. That's 1 to 1. If I graph this function, it's just a straight line. It will pass the horizontal line test, right? Okay, so y plus 1 equals 2x. X equals 1/2 y plus 1/2. Okay? So if it's 1 to 1, then I can just borrow the PMF for x, right? And, okay, 1/3 stays as it is. If x took values minus 1, 0, and 1, then what values does y take? Minus 3, minus 1, and 1. Okay? Okay, so that one's fairly easy. Okay. So now we come to continuous distributions. If I have a continuous random variable x, it has a PDF, f sub x. And then if I have a random variable y is equal to f of x, is there some way to go from the PDF for x to the PDF for y? Okay. Okay, so we have a similar result. In the case of in the special case of a 1-to-1 transformation, we have a similar result. For more general transformations, it might be easier to first find the CDF for y first, and then take its derivative to find the PDF for y. Okay, we'll do that later. Let's just first we do the special case of a 1-to-1 transformation. Okay, so once again, if x is a continuous random variable, it has a PDF f sub x. Y is the function of x. Y is equal to u of x. If u is 1 to 1, then we think about its inverse, let's say v, and we write x is equal to v of y. So we're going to be replacing x by v of y. Okay? All right, just there's one technicality. Okay? So your f sub y is going to be equal to f sub x evaluated at v of y, right? Remember, x was equal to v of y, times the absolute value of the Jacobian j, and in the one-dimensional case, j is equal to the derivative of the inverse transformation evaluated at y. Okay? The reason is that this is like doing, you're doing an integration. So when you're doing integrations and you do a change of variables, right? The differential part, the d something part, changes, right, as you go from one, as you do your substitution. So think of it that way. Okay.
So is there a proof for that?
Is there a proof for that? Yes, there's a proof for that, but I'd rather not do it in this course. All right. Let's suppose that we've got this x, it's continuous, and it takes values between 0 and 1. Okay. So for x, let's say here, so let's say that that's y, this is the line y equals 2x. And over here, the PDF takes 0 values. And over here, the PDF takes 0 values. Okay? Now, I'm going to transform to a new, I'm going to have a new random variable defined in terms of the random variable x. So I'm going to say that y is equal to 2x minus 3. Okay. Is that a one-to-one transformation? Sure. If I were to graph that thing, you could apply the horizontal line test, right? So this has an inverse, right? So I can say 2x is equal to y plus 3. X is equal to 1/3 y plus 3 over 2. Okay? Okay, so we agreed that it was one-to-one, and we found the inverse transformation. Is that okay? So the inverse transformation, right? This is my, right? If I call the forward transformation u, then the inverse transformation is v of y, and that gives me x. Is that okay? Now, what's the derivative of this inverse transformation? Oh, sorry, this was not 1/3. So it's 1/2. Okay? What's the derivative of v with respect to y? 1/2? Okay, so the magnitude of the Jacobian, sorry, the absolute value of the Jacobian is the absolute value of v prime of y. The absolute value of 1/2 is 1/2. Is that okay? All right, so this says then that you have to replace x by v of y in here, and you have to multiply by this term, the absolute value of the Jacobian. Okay. So right, multiply by the absolute value of the Jacobian. Get that? Okay. So f sub y of y 2x is, in terms of y, it's y plus 3. Okay? X is replaced by 1/2 y plus 3/2 times the 1/2 you got from the Jacobian. Right? And then you have 2 times that. Right? Okay. V of y times the absolute value of the Jacobian is, V of y is 1/2 y plus 3/2 times the Jacobian was 1/2. Okay? Because you want to get everything in terms of y. And this is like a change of variables in an integral, so you have to also have a Jacobian when you do a substitution, basically, use substitution. Okay? And now, this is my x. That's my x. So what's 2x? 2x is y plus 3 over 2. So we want to replace that 2x by y plus 3 over 2. Is that okay? All right. X was going from 0 to 1. So how is y, what's the range for y? If x takes values from 0 to 1, and y is equal to 2x minus 3, then y takes values from minus 3 to, right? Minus, okay, so when x is 0, this is minus 3. And when x is 1, this is minus 1. Okay? So we need to replace that over there. We have the range for x. You have to replace it by the range for y. And you can leave the 0 alone. So when you do all of that, I think this is what you get. Oh. I may have forgotten to multiply by 2 in this case. Okay, anyways, check my arithmetic.
The one on the board is the correct.
I think so. Okay. Okay, and once again, this little bit down there, 0 otherwise, you've got to specify that, right? Okay. So then you say, well, okay, that's all well and good. There's a nice formula when you have a one-to-one transformation. Are you guaranteed to have a one-to-one transformation? No, you're not. Okay? So what should you do? So another approach, and this would work whether the transformation was one-to-one or not, right? Another approach is don't find the PDF for y directly. Find the CDF for y first, and then take its derivative to find the PDF for y. Okay, and this is how you do it. Okay. So, continuous random variable x, it has a PDF f sub x, and it has some CDF that from capital F sub x, If you aren't given the CDF, you could calculate it from the PDF for x, let's say. And you've got y is a function of x, not necessarily one-to-one. Then it has some CDF and PDF also, and we'd like to find those. Okay, and you have to keep in mind, what do you mean by the CDF? By the CDF for y, I mean the CDF evaluated at y is the probability that the random variable y takes a value less than or equal to y, or takes a value from minus infinity to y. Okay. What's y? Y is equal to g of x. Y was some function of x. So the CDF evaluated at y is the probability that g of x is less than or equal to y. Okay? But what's the probability of g of x is less than or equal to y? Well, you find that by integrating over all the x's such that g of x is less than or equal to y. You integrate the PDF for x. Right? Right? So if g of x is less than or equal to y, then x must lie in some range where g of x is less than or equal to y. Okay? We'll do a specific example. Hopefully it'll be clear. Okay? Now that you found the PDF, now that to find the PDF for y, you differentiate the CDF for y. Okay? Let's do a particular example. We have a uniform PDF. So f sub x on 0, 1. Okay? So x is uniform on 0, 1. So what value does it take? It's uniform. It means it's constant from 0 to 1. And outside of the interval 0, 1, it is 0. And it has to integrate to give you 1, right? So probably shouldn't draw the vertical lines, but anyways, right? Yeah, so 0 to 1. So what should this height be here? If I integrate 1 on the interval from 0 to 1, I get 1, right? Okay, so there's your PDF. That's the graph of the PDF, okay? All right. Uniform, continuous uniform means the PDF has a constant value on an interval, and it takes a value 0 outside of the interval. Now that constant value has to be such that when you integrate that constant over the interval, you get a total probability of 1. Okay? So if it's uniform from 0 to 1, its height would have to be 1. Right? If I integrate the area of the unit square, basically, is 1. The integral of the PDF has to give 1. Because it's a total probability, right?
How do you know height?
Huh?
I know that the probability underneath the area is 1. I know that.
Yeah.
I don't get the height.
Oh, well, okay. So, okay, so it's uniform, which means it has to be constant on the interval. Okay? So 0 to 1. But this is the total probability, right? If I integrate it from minus infinity to infinity, this would give me all zeros. This would give me all zero. So then the only part here is here. Okay, so this has to be equal to 1 for this to be a PDF. Okay? All right. So let's define a transformation. Y equals exponential of x. So how do I find the PDF for y? Well, okay, let's recall this is the PMF. It's the uniform distribution on 0, 1. Okay. Now let's find its CDF. Okay, so how do you find the CDF from the PMF? You integrate. Okay, so what's the probability of taking a value less than 0? 0. What's the probability of taking a value less than 1? Well, all the probability is here, so it's 1. Okay? So now what's the probability of, say, some value t in here? It's the integral from x equals 0 to x equals t, the PDF, which is 1, dx. So what's that? That's x evaluated at 0 and at t. So that's t. Okay. So the PDF, there's no probability that it lies between minus infinity and 0. There's a value x that it lies between 0 and 1. And then anywhere past 1, yes, it's the value that it's taken, which is in here, is definitely less than this value over here. Okay? Okay, so that's f sub x. All right, let's look at what's happening. So x is taking values from 0 to 1. So what values is y taking? Y was the exponential of x, right? Yeah, so 1 and e, right? Now, okay, so let's go through this carefully. The probability that y takes a value less than y, well, that's the CDF, right? So in order for y to take a value less than or equal to y, well, what was y? Y was the exponential of x. So y should take exponential of x should take a value less than or equal to y. Well, if the exponential of x is less than or equal to y, then x itself is less than or equal to the logarithm of y. So the PDF for y evaluated at y, sorry, the CDF is the well, this is just the CDF, the probability that x is less than some value. So this is the CDF evaluated at logarithm of y. Okay? Okay, so once again, we don't need to worry about 0. We don't need to worry when it's, well, if x is bigger than 1, that means that y is bigger than e. Okay. If x is between 0 and 1, then between 1 and e, y is between 1 and e. if x is less than 0, then y, which is the exponential of x, is less than 1. Okay? So we put all that in. And what was x in terms of y? Y was equal to e to the x, so x was equal to the logarithm of y. Okay? So everywhere I replace x by logarithm of y. All right? And now I can take the derivative. I have the CDF for y, so I can find the PDF by taking the derivative of the CDF. Okay? So there you go. Okay. This? Okay. So if I take the derivative of 0, I get 0. I take the derivative of log y, I get 1 over y. Take the derivative of 1, I get 0. Right? Okay. Okay. And, I could write this as, well, log y less than 0, I might write it as y less than 1, for example. Okay. Okay, then. And because the transformation is 1-to-1, we could have just gotten this from the formula. But, there are going to be transformations which are not 1-to-1, and you should, right? So the exercises that I've uploaded, look at the ones that are not 1-to-1 transformations.